Hey, what's going on, guys? In this video we are going to see an example on first order transient circuits. First of all, to make sure whether this is a transient circuit, you can see this switch right here. So when you see something like this is definitely a transient circuit. And to make sure whether this is a first order transient circuit, we look for a energy storage device. And here, if you look at this diagram, here we have a capacitance. Capacitance is an energy storage device, so this is definitely a first order transient circuit. Now also you have to remember that all the first order linear system can be modeled by this differential equation, that is x of t is equal to x infinity plus x naught minus x infinity e power negative t minus t naught over tau, right? So this is what we are going to do. In the final answer we are going to give the answer in terms of this first order differential equation. Now, in order to do this one, we had to find these four terms. We had to find what is the x at infinity. So this is basically the voltage. This is what we are interested in. The voltage at this point at infinity, and also voltage at this point at when the time is equal to 0. And also we had to find the initial time and the tau. Tau is RC. Since we are trying to find 1 over tau, in the differential equation we have to give it this one in terms of 1 over tau. We can find that in that pattern too, right? Tau is basically R times C. R is resistance times the capacitance. Now let's go ahead and begin with the easy part. So let's list all the value we should find. We have to find x infinity, and we have to find x0, and also we have to find the t0, and also we have to find tau, but let's find 1 over tau, so we can express this one in the first order differential equation easily, right? Now let's go ahead and solve this one. First of all, what I like to do is I like to combine this energy source into one. I want to keep it as one source. You can do this by, if you remember that when we have capacitance in parallel, we can directly add them, and when it's in series we just multiply and let's see. So here we have 12, 6 plus 6, that's going to be 12, right? 12, and then 6 is in series right now. Now to combine to find the equivalent capacitance, what we do is we just multiply 12 times 6 divided by 12 plus 6, and that's going to give us 12 times 6 is going to be 72 divided by 12 plus 6, that's going to be 18, and that's going to give us 4, right? This is going to be 4. So the equivalent capacitance we are going to have is 4 microfarad. Now we can go ahead and draw our new diagram. Okay, in the new diagram we are going to have, okay, let's get rid of this. Okay, in the new diagram we are going to have this 12 voltage. Okay, this 6 ohm right here, 6 kilo ohm, and then I combined all these microfarads into one, so that's just 4 microfarad. Okay, so this is going to be just 4 microfarad, and in the other side we have 2 kilo ohm right here, 2 kilo ohm. Okay, this should be 2 kilo ohm. This is 2 kilo ohm, and then here we have 4 kilo ohm. 4 kilo ohm, and then we have voltage across this V naught T. Okay, now we have made combined this one into, we have turned this one into single energy storage device, right? Now let's start with the easiest part. T naught is going to be always 0. Like most of the time it's going to be 0. One case it won't be 0 is when you deal with a unit step function. In that time you will be asked to do the time in particular time, like it won't be 0 sometime. So most of the time it's going to be 0, so that's the easiest part. And let's go to the next part. Next easiest one is going to be the tau, calculating this time constant, 1 over time constant. And here what we can do is, if you think about this, I also put the switch right here to illustrate this one better. This switch. Okay. So this, we have this switch, and this is t is equal to 0. Okay. So after t is equal to 0, when t is greater than 0, we are going to open this switch, right? When t is greater than 0, we are not going to have this part, because when we open the switch, this is nothing, right? So we are only going to have this one right here. So let's draw that one right here. So we are going to have this capacitor, and we can find the R Thevenin by simply adding these two resistors right now. 2 kilo ohm, and here we have 4 kilo ohm. Both of them are in series. Therefore, R Thevenin is going to be, instead of putting like this, we can just put, I just write this one, right? So 2 kilo ohm, and this is 4 kilo ohm. So the R Thevenin is going to be just 6 kilo ohm. Both of them are in series, so if you add them together, you will get R Thevenin 6 kilo ohm. So if R Thevenin is 6 kilo ohm, we know that time constant is RC, and we are trying to find 1 over tau. So 1 over tau is going to be equal to 1 over RC, and 1 over R is 6 kilo ohm. 6 kilo ohm, and the capacitance right here is 4 microfarad. 4 microfarad, and if you calculate this value, you should get 41.67. So this is 41.67. So this is our 1 over tau value, 41.67. Now let's look at what happened to the voltage when the time is infinity. Now if you think about that, before we had, now let's see what happens the time is before less than 0. So when the time is 0, we had this battery, and this one was connected together. So what happens is, this power through the battery, like the current passes everywhere, and the current goes through these capacitors, and the energy will be stored fully, right? So once the energy is fully stored, this will be, once the energy is fully stored, what's going to happen is the current will just go through these resistance, and it will keep going like this, right? Then this one, there won't be current going through this, and after it opens, what will happen is, this one acts as a battery, like the current from this capacitance will flow through this resistance, and when the time is infinity, it means after a long time, this is the energy from this capacitor is going to dissipate due to the resistance. It's going to be zero, like it's going to lose all the energies. So at the end, we are going to have everything zero, like voltage is also going to be zero. So we can say that x infinity is equal to 0. Okay, now let's see what happened when the time is 0. What happened to the voltage when the time is 0? So when the time is 0, we can find the voltage across these capacitance. It will be helpful to find out the voltage across this 4 kilo ohm resistance. So first let's go ahead and find the voltage across this capacitance. Now to find that, I'm going to draw a new diagram like this. So here we have plus minus 12 voltage, and here we have, so when time is equal to 0, this is closed, so we deal with this, we don't consider the switch, we just treat it as a full circuit. This is 6 kilo ohm right here, and then here we have the 4 microcoulomb. So we are trying to find the voltage across this capacitance. So let's call that one VC. Okay, and then we have this 2 kilo ohm resistance, and also So now let's avoid this capacitance thing for now. Let's put it as plus minus VCs, right? V capacitance, and here we have 2 kilo ohm, and also we have 4 kilo ohm right here. And you can see that these three are in series, these three resistors are in series. So if we add them together, that's going to be 6 plus 2 8, 8 plus 4 12. So we are going to have 12 kilo ohm, right? 12 kilo ohm. Here we have 12 voltage, and we know that I is equal to V over R, and 12 voltage divided by 12 kilo ohm, that's going to give us 1 milliampere. So we have the current flowing through this circuit is going to be 1 milliampere. So from that one we can solve for this VC, because we know that 12 minus this VC over the resistance in between, that is 6, should be equal to 1 milliampere, right? And if you solve for VC, you should get this value, that is 6 voltage, right? If you solve for VC, you will get 6 voltage. Now after you find the VC, it's easy to find the V across this 4 kilo ohm resistance. To find that, what you do is so let's write that one down first. V0 T is going to be equal to 6 voltage times the resistance at that one, that's 4, over the total resistance, that's going to be 2 plus 4, that's going to be 6. But to better illustrate this one, it's better to draw a diagram, right? So like before I do that, I draw a diagram for this one, so you can see that. Okay, to draw the diagram, I erase this one. Okay, we need this differential equation for large part. Okay, I draw the diagram right here. So here we consider this one as open, and this is our capacitance. Okay, then we have 2k ohm resistance, and here we have 4 kilo ohm resistance, and we are trying to find the voltage across this 4k ohm resistance. So V naught is what we are trying to find, and from this one we can see VC, we found out voltage across this one, we found out that 6 voltage. Now to find VT, we can say that V naught T is going to be equal to 6 voltage times the resistance of this, that is 4 kilo ohm, over the total resistance 4 plus 2, that's going to be 6, and if you multiply, that's going to be just 4 voltage, right? So when the time is equal to 0, we are going to have 4 voltage, and that's what we found out right here, 4 voltage. Now we can go ahead and express our final answer in terms of this linear first order differential equation, that is given by x of t is equal to x infinity plus x0 minus x infinity e power minus t naught over tau. And let's write this one. So x infinity we found out 0, so we don't have to worry about this part. X0 we found out 4 voltage, so let's put 4 right here, minus x infinity, that's again 0, and e power minus t, we don't have t, so we keep that t as it is, and t naught we found out that is 0, so that's going to be eliminated. And tau we found out 1 over tau is 41.67, so when we express, we just put minus, because we have minus sign in front of this t, minus 41.67, and also we have t remaining, right? 1 over tau is this value, so I just directly put the value, and this is going to be our final answer when the t is, and this is in terms of voltage, and this is when the t is greater than 0. and that's our final answer. I hope this helps. Thanks for watching.